In the last lecture, I have introduced the axiomatic definition of probability. This takes care of the deficiencies or drawbacks left by the classical definition or the relative frequency definition of probability. So, in this definition, we give a general framework under which a probability function is defined. This does not tell you how to calculate a probability, but a probability function must satisfy these axioms in order to be a proper probability function. So, in particular, if we have a sample space and a sigma field of subsets of that sample space, let us call it script B, then a set function P from B to R is said to be a probability function if it satisfies the given three axioms, which we name P1, P2, P3. The first is the non-negativity axiom, that is the probability of A is greater than or equal to 0 for all A belonging to B. So, this is the axiom of non-negativity. Then probability of the full sample space is 1. Basically, it makes the P to be a finite function. And the third axiom is the axiom of countable additivity, that is, for a given pairwise disjoint sequence of sets, probability of the union is equal to the sum of the individual probabilities. Thus, this omega B and P is called a probability space. Now, some of the consequences of the axiomatic definition are as follows. The first consequence is, let me call it C1, that probability of the impossible event must be 0. To prove this statement, let us take A1 is equal to, say, omega and A2, A3, etc. to be phi in axiom P3. Then we will get probability of omega is equal to probability of omega plus probability of phi plus p of phi plus p of phi, etc. Since p omega is 1 and P1 implies that p phi is greater than or equal to 0, we must have p phi equal to 0. The second consequence is that for any finite collection A1, A2, An of pairwise disjoint sets in B, probability of union AI I is equal to 1 to n is equal to sigma probability of AI I is equal to 1 to n. Let me explain this, that why do we need this finite additivity consequence here to be proved. We have assumed the countable additivity axiom, but that does not necessarily imply the finite additivity. A proof of this can be given using the fact that in A3 we can take An plus 1, An plus 2, etc. to be phi in the third axiom. Then we will get probability of union AI I is equal to 1 to n is equal to sigma probability of AI I is equal to 1 to n plus p phi, etc. Now, if you use consequence 1 here, then these terms are 0 and we get sigma probability of AI I is equal to 1 to n. A third consequence is the P is a monotone function. That is, if I take say A to be a subset of B, then probability of A will be less than or equal to probability of B. Let us look at the proof of this. Consider say a set A and a set B. Then I can write B as A union B minus A, that is, this is B minus A and this is A, and these two are disjoint. So, if I make use of the finite additivity consequence, then probability of B is equal to probability of A plus probability of B minus A. Naturally, this is greater than or equal to probability of A, since probability of B minus A is always greater than or equal to 0. As a further consequence, we have that for any event A, probability of A lies between 0 and 1. Now, the first part of this is always true because of the P1 axiom. Now, A is a subset of omega for every omega for every A. This implies that probability of A is less than or equal to probability of omega, that is equal to 1. If I consider probability of A complement, then it is equal to 1 minus probability of A. This follows because I can write A union A complement as omega, and therefore probability of A plus probability of A complement is probability of omega, that is equal to 1. Now, we look at certain further consequences of the definition. The first of them is the addition rule. For any events A and B, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. In order to prove this statement, let us consider any two sets A and B. Then A union B can be expressed as A union B minus A intersection B. So, we can write A union B as A union B minus A intersection B. We can observe here that this is a disjoint union. Therefore, if I consider probability of A union B, it is equal to probability of A plus probability of B minus A intersection B. Now, at this stage we notice that A intersection B is a subset of B, and if we look at the statement that probability of B is equal to probability of A plus probability of B minus A, then this implies that probability of B minus A is equal to probability of B minus probability of A. That means, if A is a subset of B, then probability of B minus A can be expressed as probability of B minus probability of A. Therefore, here we can write this as probability of B minus probability of A intersection B. Now, naturally one can think of the generalization of this rule. For example, if I consider say for 3 events, suppose A, B and C are 3 events, then we must have probability of A union B union C is equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of C intersection A plus probability of A intersection B intersection C. one can look at this statement from the point of view of set theory or Venn diagram. If I consider three events, say A, B and C, then the union can be expressed as A union B union C. However, here we have to remove A intersection B, B intersection C and C intersection A. If we remove that, then the set A intersection B intersection C has been removed 3 times. So, we have to add it once to get this portion here. So, A intersection B intersection C has to be added here. So, this gives us a rule for considering a general addition rule, and we have the following result: general addition rule. So, if we have events A1, A2, An, then probability of union Ai, I is equal to 1 to n, can be expressed as sigma probability of Ai, I is equal to 1 to n, minus double summation probability of Ai intersection Aj, I is less than j, plus triple summation probability of Ai intersection Aj intersection Ak, I less than j less than k, minus and so on. Finally, you will have minus 1 to the power n plus 1 probability of intersection Ai, I is equal to 1 to n. One can prove this result using induction. For example, if we take n is equal to 1, the result is trivially true. For extension from k to k plus 1, we will need the result for n is equal to 2, which has already been proved. For n is equal to 2, we have addition rule. Now, assume that the result to be true for n is equal to k. Now, take n is equal to k plus 1. So, we need to consider probability of union Ai, I is equal to 1 to k plus 1, and we can consider it as probability of union Ai, I is equal to 1 to k union Ak plus 1. So, now I can apply the result for the union of A and B, 2 events. So, this becomes probability of union Ai, I is equal to 1 to k, plus probability of Ak plus 1 minus probability of union Ai, I is equal to 1 to k intersection Ak plus 1. Now, the first part of this can be expanded, because we have already assumed that this rule is true for n is equal to k. So, this becomes sigma probability of Ai, I is equal to 1 to k, minus double summation probability of Ai intersection Aj, I less than j. Now, these sums are up to n, triple summation probability of Ai intersection Aj intersection Ak, I less than j less than k, the sums are up to n, and so on, plus up to minus 1 to the power k plus 1 probability of intersection Ai, I is equal to 1 to k. Now, then we have probability of Ak plus 1, and here we apply the distributive property of the unions and intersections. So, this becomes minus probability of union A I intersection A k plus 1 I is equal to 1 to k. Now, if you look at this last term, it is again union of k events, and since we have assumed the probability of union result to be true for n is equal to k, we can apply that formula. So, using that, we will get summation of probability A I intersection A k plus 1 for I is equal to 1 to k, and that term can be adjusted with this. So, let me write it here firstly. Sigma probability of I is equal to 1 to k minus double summation I less than j up to n probability of I intersection aj plus triple summation I less than j less than k probability of ai intersection aj intersection ak minus and so on plus minus 1 to the power k plus 1 probability of intersection ai I is equal to 1 to k. Now, this probability of ak plus 1 can be added to the first term. So, the first term becomes probability of I is equal to 1 to k plus 1. Now, let me expand the last union by using the formula for n is equal to k. So, this becomes sigma probability of ai intersection ak plus 1 I is equal to 1 to k minus now you will have double summation probability of ai intersection ak plus 1 intersection with aj intersection ak plus 1 where I is less than j and the sum goes up to n only, goes up to k. So, I think I have made some small mistakes here. These sums are up to k. Then you will have triple summation I less than j less than k probability of ai intersection ak plus 1. So, we may put it as r intersection a j intersection ak plus 1 intersection a r intersection ak plus 1. And so on minus 1 to the power k plus 1 probability of intersection ai intersection ak plus 1. Now, let us look at the terms. The term sigma probability of ai intersection ak plus 1 can be combined with this term here with a minus minus getting adjusted, and therefore, if you see here, now we already had all the intersections up to k. Now, we have a1 intersection ak plus 1, a2 intersection ak plus 1 and ak intersection ak plus 1. So, this gets adjusted here and you will get a term. So, the first term remains as such probability of ai is equal to 1 to k plus 1. In the second term, you will get I less than j, and now the summation is up to k plus 1 probability of ai intersection aj. Now, let us look at this term. This term is ai intersection aj intersection ak plus 1, where I and j's are varying from 1 to k, and if we look at the third term in the previous expression, here we had all the intersections of 3 sets up to k. So, this term gets adjusted in this one and you will get plus triple summation probability of ai intersection aj intersection al ar I less than j less than r up to k plus 1. In a similar way, if I look at this term here, it will be intersection of the 4 terms, and the last set is a k plus 1. That means it is taking care of all the terms of the intersection taken 4 sets at a time. So, in this way all of the terms are combined. If you look at this term, this is actually intersection of all of the ai's from I is equal to 1 to k plus 1, and since there is a minus sign outside of the square bracket, this becomes minus 1 to the power k plus 2. So, you will get minus 1 to the power k plus 2 probability of intersection I is equal to 1 to k plus 1. Hence, the result is true for all positive integral values of a. Let us look at the some applications of this one. Before giving the application, let me also consider the limit of the probabilities or probability of the limit. As I mentioned that we have defined monotonic sequences, and for the monotonic sequences of the sets the limit always exists. So, we have the following result for monotonic sequences of the sets. We have the following theorem: if an is a monotonic sequence of sets in B, then probability of limit of an is equal to limit of probability of an. To prove this result, let us consider an to be, say, monotonically increasing sequence. Let an be monotonically increasing sequence. If that is so, then limit of the sequence an will become union of n is equal to 1 to infinity. In order to prove that, we have to look at probability of limit means probability of the union. Now, what we do, we decompose this union by defining a new sequence of sets by saying, say, B1 is equal to A1, B2 is equal to A2 minus A1, Bn is equal to An minus 1 for n greater than or equal to 2. If we look at this one, basically what we have done, the sequence of sets is like this. This is, say, A1, this is A2, this is A3 and so on. So, if I look at the union of AIs, we are decomposing it as a disjoint union. This A1, A2 minus A1 will be this portion, then A3 minus A2 will be this portion. So, we will have that Bn is a disjoint sequence of sets, and an is equal to union of bi from 1 to n. Naturally, this implies that probability of an is equal to probability of bi sigma I is equal to 1 to n. Now, if we look at limit of the sequence an as n tends to infinity, then it is equal to limit of union bi I is equal to 1 to n tending to infinity, which is equal to union of bn n is equal to 1 to infinity, because union bi is a monotonic increasing sequence and the limit will be the ultimate union of these sets. So, if I look at probability of limit of an as n tends to infinity, then it is equal to probability of union bn n is equal to 1 to infinity. Now, bn is a disjoint sequence of sets, then by the axiom of the countable additivity, this becomes probability of sigma probability of bn n is equal to 1 to infinity. Now, this we can write as limit as n tends to infinity sigma I is equal to 1 to n probability of bi, which we can write as probability of union of bi I is equal to 1 to n, which is equal to limit as n tends to infinity probability of a n. So, thus we have proved that probability of a limit of a sequence of monotonic sequence of sets is equal to limit of the probability of the sequence of the sets. We may also consider the case of monotonically decreasing. Now, that can be obtained by taking the complementations here, or you can define in a reverse way. The probability function we are assuming to be countably additive, but countably additive axiom implies that if we have a disjoint sequence, then the probability of union is equal to the sum of the probabilities. What if we do not have disjoint sequence? For example, if I have two sets, say A and B, then we have probability of A union B is equal to probability A plus probability B minus probability of A intersection B. So, that means if I remove probability of A intersection B from there, then we get probability of A union B less than or equal to probability A plus probability of B. This is called subadditivity. So, if in general if we consider any sequence of sets, then the probability of union will be less than or equal to the sum of the probabilities. So, we have subadditivity of the probability function. We can state it in the form of a theorem. For A1, A2, An belonging to B, probability of union I is equal to 1 to n is less than or equal to sigma probability of I is equal to 1 to n. So, one can prove this by induction, because for n is equal to 1 the result is true, and if we look at for n is equal to 2, it is already shown to be true. So, for n is equal to 1 the inequality is trivially true. For n is equal to 2, which we will require for extension from k to k plus 1 case. So, for n is equal to 2, the inequality follows from the addition rule. So assume it to be true for say n is equal to k. Now for n is equal to k plus 1, we can write probability of union ai is equal to 1 to k plus 1 as less than or equal to probability of union ai is equal to 1 to k plus probability of ak plus 1 by using the result for n is equal to 2. So now on this we can make the use of assumption that up to n is equal to k it is true. So it becomes less than or equal to probability of ai is equal to 1 to k plus probability of ak plus 1, which is nothing but the sum of the probabilities I is equal to 1 to k plus 1. Therefore by induction the result is true for all of them. Now if we want to prove the result for a countable number of these, then we can consider the decomposition. So if we have for any countable sequence say ai in B, probability of union ai is equal to 1 to infinity is less than or equal to sigma probability of ai is equal to 1 to infinity. In order to prove this one may consider the decomposition of union ai into a disjoint decomposition in the following way. Let us define say b1 is equal to a1, b2 is equal to a2 minus a1, b3 is equal to a3 minus a1 union a2, and so on. In general, bn is equal to an minus union of ai is equal to 1 to n minus 1. If we consider a Venn diagram, then it will be clear that what sets we are defining. Suppose these sets are a1, a2, a3, a4, etc. Then a1 and then a2 minus a1 is this set, then a3 minus a1 union a2 becomes this set, a4 minus a1 union a2 union a3 becomes this set. So naturally you can see here that we are considering the union as a disjoint union. So then bn is a disjoint sequence of sets. Further, union of ai is equal to 1 to infinity is equal to union of bi is equal to 1 to infinity. To prove this, let us observe that union of bi is already a subset of union bi, because each of the bi's is a subset of the corresponding ai's. Now any point of ai, let us consider say x belonging to union of ai. Let j be the smallest index so that x belongs to aj. Then x will belong to bj. Consequently, x will belong to union of bi's. As a result, since union of Bi is already a subset of union of Ai. We are now getting union of Ai is a subset of union of Bi. Therefore, we must have union of Ai is equal to union of Bi's. So now, if we consider probability of union of I is equal to 1 to infinity, it is probability of union of Bi I is equal to 1 to infinity, which is less than or equal to, which is actually equal to sum of the probability of Bi's, because Bi's are now disjoint and we can use the axiom of countable additivity. Now each Bi is a subset of Ai, therefore probability of each Bi is less than or equal to probability of Ai. Therefore, this becomes less than or equal to sigma probability of Ai, I is equal to 1. This proves the countable additivity of the probability function. We also have something called Bonferroni inequalities, which basically give that the probability of the unions are bounded between two bounds. So, for any events A1, A2, An in B, probability of the union, which is already less than or equal to sum of the probabilities, it is however greater than or equal to probability of minus let me not prove it here, the proof will be by induction. We can see the right hand side has already been proved. To prove the left hand side, if we take n is equal to 1, then it is trivially true. For n is equal to 2, there is equality by the addition rule. So, assuming for n is equal to k, if we write for n is equal to k plus 1, then we can split it into two terms, that is union of I is equal to 1 to k, union ak plus 1. On that we apply the addition rule and then apply the assumption for k. That will prove the general Bonferroni inequality. In a similar way, we have what is known as Boole's inequality. The Boole's inequality gives a relation between the intersection. Likewise, for example, if I have An is any sequence of sets in B, then probability of intersection I is equal to 1 to infinity, is greater than or equal to 1 minus sigma probability of Ai complement I is equal to 1 to infinity. To prove this, we simply use the subadditivity, because we can write probability of intersection I is equal to 1 to infinity as 1 minus probability of intersection Ai complement. Now, this can be written as 1 minus probability of union Ai complement by using De Morgan's laws. At this stage we can use the countable subadditivity. So, this will become greater than or equal to 1 minus sigma probability of Ai complement. Let me give some examples of applications of basic rules of probability. Let me start from a birthday problem. Suppose there are n persons in a party, assuming that the number of persons is less than or equal to 365, and no person has birthday on 29th February, what is the probability that at least 2 persons share the same birthday? Now, in order to analyze this problem, let us consider the set theoretic description. Let us consider A to be the event that at least two persons share the same birthday. Then if you look at this event, it is slightly complicated event in the sense that 2 persons may share, 3 persons may share, and so on, and finding out the probabilities of each of them may be a little bit complicated, because if we say 2 persons share, then which of the dates, and all others must be on some other dates and they should not be the same. Suppose we say 3 persons share, then which of the one of the 365 days, and all other persons must be on distinct days, which distinct days. So this is a complicated way to analyze. However, if we use the set theoretic representations, we can look at the complementary event, A complement. This means no 2 persons have the same birthday. Now this becomes somewhat simpler, because if we look at the probability of A complement, assuming all the birth dates to be equally likely, this number will be simply 365 Pn divided by 365 to the power n. Here the denominator denotes the total number of possibilities for n persons to have birthdays, because each person can have any of the 365 days as a possible birthday, and therefore n persons can have possible number of birthdays as 365 to the power n. If we make the assumption that none of them have the same birthday, then it becomes a problem of choosing n numbers out of 365 which are distinct. So it is nothing but the number of permutations taking n at a time from 365, that is equal to 365 into 364 up to 365 minus n plus 1 divided by 365 to the power n, which we may write as a way of representation as 1 minus 1 by 365, 1 minus 2 by 365, and so on up to 1 minus n minus 1 by 365. And so probability of A becomes 1 minus the product given by these terms. An interesting thing would be to look at that how many people are required so that at least 2 will share a birthday. If we think from a layman point of view, then we may think that the number, since the number of possible birthdays is 365 to the power n, so n should be somewhat large in order that this probability is significant. So let us look at the table of probabilities. Let us consider, say, n probability of A complement and probability of A. So, a simple calculation table can be prepared. If I have n is equal to 10, then the probability of A complement is 0.871 and consequently probability of A becomes 0.129. If we take n is equal to 20, probability of A complement is 0.589 and probability of A becomes 0.411. If we take n to be 23, then probability of A complement is 0.493 and probability of A becomes 0.507. That means with as less as only 23 persons, the probability that at least two share a common birthday is more than 50%. So, it is from a layman's thinking, this is counterintuitive. We need very few persons to, at least two of them to share a common birthday. If I take n is equal to 30, then this probability becomes 0.706. If we take 50, the probability is 0.97, and for n is equal to 60, the probability is 0.994. It is nearly 1. That means in a set of 60 people, the probability is nearly 1 that at least two of them will share a common birthday. So, here you can see that the elementary rules of probability have been used for calculation. For example, we have used the property of the complementation. To evaluate the actual probability, we have used the method of classical probability by assuming all the birth dates to be equally likely for all the persons. Let us look at some other applications of the basic rules of the probability. Suppose a die is tossed 3 times independently and the outcomes are recorded as numbers A, B and C. What is the probability that the roots of equation ax square plus bx plus c is equal to 0 are real? Now, if we want to calculate this probability, here the outcomes A, B and C are random. Each of the values of A, B and C can be numbers 1 to up to 6. Therefore, the quadratic equation ax square plus bx plus c is equal to 0 will have the real roots if b square minus 4ac is positive. So, we have to look at the number of cases where b square minus 4ac is greater than or equal to 0. So, this has to be done through an enumeration, and we can prepare the table that what are the possibilities of b and therefore, the corresponding values of b square, what are the possible values of a and c which lead to 4ac being less than or equal to b square. So, let us take say b is equal to 1, then b square is equal to 1. That means there is no case which will give me 4ac to be less than or equal to b square. So there is no possibility here. So if we look at the number of cases, this is 0. If we take b is equal to 2, then b square is equal to 4, and if I consider a and c to be 1 1, then 4ac will become 4. So there is one case which will give me b square greater than or equal to 4ac. If we consider b is equal to 3, then b square is equal to 9. Now 1 1, 1 2 and 2 1, there are 3 cases which will give me b square greater than or equal to 4ac. If we have b is equal to 4, then b square is equal to 16. We will have the cases 1 1, 1 2, 2 1, 2 2, which will correspond to 4. So 1 4, 4 1, 1 3, 3 1, 1 2 3 4 5 6 7 8 cases are there which will give me b square greater than or equal to 4ac. If we have b is equal to 5, then b square is equal to 25. Then all the above cases, that is 8 cases, plus we will also have 1 5, 5 1 and possibly 1 4 4 1. So we will also have 1 6, 6 1, 2 3, 3 2, basically 1 2 3 4 5 6 more cases. So 14 cases are there. If I have b is equal to 6, then b square becomes 36, and all the 14 cases, plus we will also have 2 4, 4 2, then 2 5 is not possible, 3 3, I think 3 3 must have come here itself, because no, it will not come here. 3 3 will come here because this will give me 9. So there are 17 cases. So if you look at the total number of cases, it is 39, 42, 43 cases are there. Total number of cases is 43, and the total number of possibilities, if I define A to be the event that the roots are real, then the probability of that will be given by the favorable number of cases divided by the total number of cases, which is 6 cube here, because 3 dice, each of them have 6 possibilities. So the total number of possibilities are 6 cube, that is 43 by 216. Likewise, in this problem we may also find out the probability of the quadratic equation to have complex roots, or the real roots but equal, etc. We may consider all types of possibilities. So I will end today's lecture by this. Thank you.